So I want to thank the organizers for organizing this wonderful conference and inviting me to speak. So this is based on joint work with David Conlon and Jacob Fox. So I've given this talk a few times before, but it's the first time with both Ben Green and Terry Tell sitting in the audience. This is... all right, it's stuck. Okay. So about 10 years ago, they proved the spectacular theorem that the prime numbers contain arbitrarily long arithmetic progressions. So this is one of my favorite theorems in mathematics. I learned about it when it was first announced. I was still a high school student back then, and at the time, I felt this was such a beautiful statement, but of course the mathematics involved was far beyond my understanding at the time as a high school student. Now that I know a bit more math, I want to use this talk to explain to you some of the ideas involved in the proof of the Green-Tao theorem, and also discuss our work which simplifies a key component in the proof. So I first need to tell you about another result, which is Szemeredi's theorem, proved in the 70s, that every subset of the positive integers with positive density contains arbitrarily long arithmetic progressions. So this is a very deep result. There are now several modern approaches, but none of them are easy. And it is used as an important key input, as a black box input to the proof of the Green-Tao theorem. Now, the Green-Tao theorem does not follow trivially as a consequence of Szemeredi's theorem, because we know that the prime numbers, by the prime number theorem, have density decaying as 1 over log n. So the density of the prime numbers is 0. So, well, as an aside, so it's believed by people of this community that, and their famous conjecture of Erdős, that the density of the prime numbers alone should guarantee the existence of long arithmetic progressions. But this conjecture is still open even for 3 terms. But that is not the approach taken by Green and Tao. So instead, they use what's known as a transference principle strategy. And it goes roughly as follows. We start with a set of prime numbers denoted P. And they embed P in a slightly larger set, Q. And for the purpose of this talk, you can think of them as almost primes, or numbers with few prime divisors. Okay, that's a bit of a lie, but it's a good image to keep in mind for the purpose of this talk. And P sits inside Q as a set of positive relative density. The proof in the Green-Tao paper has 2 parts. In the first step, they prove what's known as a relative Szemeredi theorem. Informally speaking, this says that if you start with a set S, so S is placed as Q here, and if S satisfies certain pseudorandomness conditions, then it has the property that every subset of S with positive density should contain long arithmetic progressions. In the second step, they construct such a superset of the primes and verify that the superset satisfies these pseudorandomness conditions. And for the second part, they credit some of the number theoretic inputs to Goldstern and Yildirim, who are working on the problem of prime gaps at the time. So for this talk, we'll just look at this relative Szemeredi theorem. So in this informal statement, what does pseudorandomness condition mean? So Green and Tao required 2 pseudorandomness conditions, which they called linear forms condition and correlation condition. I'll describe in much more detail what the linear forms condition is, but the correlation condition is a slightly more technical condition that feels somewhat less natural for the purpose of this problem, and almost feels like it shouldn't belong here. Now, this is an interesting problem in its own right. It's an interesting result in its own right, and a natural question that one could ask is, does it hold under weaker and more natural hypotheses? Right? So this relative Szemeredi theorem, what pseudorandomness condition do you really need to have the property that every dense set contains long arithmetic progressions? Our main result is that, in fact, we can use a weaker version of Green-Tao's linear forms condition and completely get rid of the correlation condition. So this is both a simplification and also a strengthening of the relative Szemeredi theorem, which plays a main role in the proof of the Green-Tao theorem. To recap, so we saw Szemeredi's theorem, where you start with a set of positive integers, and the conclusion is that dense sets contain long arithmetic progressions. And relative Szemeredi theorem, the host set, we replace the integers by some sparse subset of the integers. So this is the sparse setting. To put our work in some context, you can ask, what sort of host set would you consider? Well, natural candidate is, well, let's take a random set as a host set. So numbers from 1 to n, I pick each number to be in my set with some probability. And this probability decays with n, so that it's a sparse set. You can ask, well, does that have the property that relatively dense subsets contain long APs? So this problem was investigated initially by Kohayakawa, Ruchak, and Roth, and they solved this problem in the case of 3-term arithmetic progressions. And they identified the correct threshold, with the correct exponent for which this phenomenon occurs. And this problem was solved in general independently by Colin Gowers and also Schacht, where they solved this problem completely for all k-term APs. For us, we'll focus on the pseudorandom case. So we'll prescribe some pseudorandomness conditions to the host set. And as I mentioned, so in the Green-Tao paper, they required 2 different conditions called linear forms and correlation, and will show that a weaker form of what they call linear forms is sufficient to guarantee the relative Szemeredi theorem. Yep.
So if you pick a random set of the lower density, does it have the linear form condition?
It does, but with a worse exponent. Yeah. Okay. So the first half of the talk, I will describe to you what is this linear forms condition. But to do this, I want to first recall a proof of Roth's theorem. So Roth's theorem is the 3-term case of Szemeredi's theorem. It says that, okay, so this is what it says. It's just a 3-term case. It was proved by Roth using Fourier analytic methods, but I want to show you a proof found in the 70s that goes through graph theoretic methods. And the reason for showing this proof is that there's a graph theoretic construction that will be very useful for motivating the linear forms condition. So, okay, so the Roth's theorem is about subsets of 1 to n, but it will be easier and equivalent to work instead in a cyclic group, Z mod n. So these 2 objects, the systems are very similar. One difference is that a 3AP, so 3-term arithmetic progression, might wrap around in a Z mod n, whereas I don't want that to happen in 1 to n. And there's an easy way to get rid of this issue, which is that you embed your 1 to n in a somewhat larger cyclic group so that these wraparounds don't occur. So it will be equivalent to work in a setting of a cyclic group, and we'll do that from now on. Okay, so here's a proof of Roth's theorem. So I construct for you, based on the set A tripartite graph, GA. It has 3 vertex sets, x, y, and z, all of them having n vertices labeled by elements of Z mod n. I put in an edge between x and y if and only if this expression 2x plus y is in my set A. Okay, so that's just the rule for putting in the edges, and you can think of this as a modified Cayley graph. I put in an edge between x and z if x minus z is in my set A, and between y and z if minus y minus 2z is in my set A. Okay? And so these are the rules for putting in the edges. Now, note that a triangle in this graph corresponds to these 3 linear forms all being in the set A. And the reason for choosing these particular linear forms is that they form a 3-term arithmetic progression with common difference minus x minus y minus z. So this says that triangles in this graph correspond to 3-term arithmetic progressions in the set A. But we started out with a set A which is free of 3 APs. So does that mean that the graph has no triangles? Almost. Not quite. There's still some triangles, namely the triangles corresponding to trivial 3-term arithmetic progressions, those with common difference 0. So you still see some triangles, but very few. And in particular, every edge of the graph is contained in exactly one triangle, namely the one which completes the equation x plus y plus z equals to 0. Okay, so this is a construction for this graph GA based on the set A, which is 3AP free. Okay, to recap, starting from A, we constructed this graph with 3n vertices, 3n A edges, so from between x and y, each vertex has A edges coming out of it, and every edge containing exactly one triangle. Okay, so there's a classic result of Rusha and Szemeredi that says that in a graph where every edge is containing exactly one triangle, then the graph must have a subquadratic number of edges. Okay, so it's a tricky result. So it follows from, it's a consequence of what's known as a triangle removal lemma. Using this lemma, we find that the number of edges must be little o of n squared, so the number of elements in A must be little o of n. And this proves Roth's theorem. Now, of course, it's a bit of a cheat because most of the meat of the proof is in this result. But I'm not going to show you this result. And also, as I mentioned, the point of showing you this proof is that I want to use this graph construction on the previous slide. Okay, so now I'm ready to describe what is this relative Roth theorem, right? So the sparse version of Roth theorem that we have. It says that if S satisfies, and I'll tell you exactly what are the pseudo-randomness conditions that we need, then it has this relative Roth property that a dense subset of S, well, so it has a property, so I'm using the contrapositive. It says that if it's 3AP free, then it has little o of S elements. Okay, and so what is the pseudo-randomness condition? Well, let's revisit this graph, but now construct the graph not on A, but based on S. Right? So somehow we know that this graph encodes the 3 APs. But okay, so again, the vertex sets are Z mod n, and I put in the edges based on whether these expressions are in my set S. So this is a graph GS. And the pseudo-randomness condition for my set S is the following. It says that this graph GS has asymptotically the expected number of embeddings of this object, K222. Yes. Meaning that if the density of S is P, then the density of embeddings of this guy should be P raised to the 12, up to 1 plus little o 1, an error. Yep?
Don't you want S also to be relatively large, or it can be as any size you want?
S is sparse. So the density of S goes down with n. Yeah. So that's the whole point, because if S is already dense, then it follows from Roth's theorem.
It can be as sparse as you want.
Not quite. I mean, there are limitations to how far you can push with this condition. Right? But yeah, so, okay. So, but we need a little bit more. Just because of technical reasons, we need a little bit more. We need that not only it has the expected number of embeddings of K222, but also the subgraphs of K222. So this guy has the number of embeddings P raised to however many edges I've drawn here. And that's the pseudo-randomness condition that I need for guaranteeing a relative Roth theorem, and that's the version that we have. Okay. Any questions?
So you stated a theorem, and then it seemed as if, do you mean what you said, or is there some extra condition that you have?
This I'll state a somewhat more precise version later on, but this is a version that's
we can understand that.
yeah. Yeah. Okay. All right. Let me try to make some arguments that this is a natural condition. It's a natural pseudo-randomness condition. And to do this, let me draw some analogies with this classic result of Chung-Graham-Wilson, which says that in graphs of constant edge density, so they stated several quasi-randomness conditions which all turn out to be equivalent. So these are things like subgraph counts or eigenvalue conditions or codegree conditions, discrepancy conditions. But in particular, there's one condition that stands out, which is that having the correct C4 count is sufficient to guarantee several other quasi-randomness conditions. And so this is a classic result of theirs. However, these equivalences fail in the sparse case. Right? They break down in the sparse case if the density of edge density goes to 0 with n. One way to interpret our results informally is that if we want some sort of extreme or Ramsey type results about some graph H, so in Roth's theorem H is a triangle, right, then we can get these results provided that there is some host graph which is pseudo-random with respect to counts of the 2 blow-up of H. So 2 blow-up, meaning I start with my graph, and then I double every vertex. And if you look at Chung-Graham-Wilson, the 4th cycle is a 2 blow-up of an edge. Okay, so this is just drawing some analogies to try to convince you that this is a natural condition to consider. So let me outline a proof of this relative Roth theorem. So this is basically the version that we saw earlier. If you have density at least delta, then the set A necessarily contains a 3-term arithmetic progression. There's a standard averaging argument credited to Bernoulli, saying that starting with this result, we can obtain a counting version of Roth's theorem, where we're guaranteed not just one 3AP, but many 3APs, a quadratic number of 3APs. And this is essentially a sampling on averaging type argument, where you, look at the progression of length n naught, and then you find a 3AP, and then you do it again, and so on. And so you get many 3APs. So let me show you how to prove Roth's theorem. Okay, so this is known as the transference principle, and it's featured in Green-Tao's work. Starting with a subset A of S, we're going to find a dense model, A tilde. So my set A originally is sparse, but there's some sense in which I can find a set A tilde, which is both a dense set and also in some ways is a good approximation for A. Okay? And this will be in terms of something that I'll call cut norm, which I'll elaborate on later on. And they also have similar densities. And furthermore, a counting lemma will tell us that the number of 3-term arithmetic progressions in my original set A, appropriately normalized, will be close to the number of 3-term arithmetic progressions in this dense model. Now, by Roth's theorem, which we'll use as a black box, the counting version of Roth's theorem, we know that there are lots of 3-term arithmetic progressions in A tilde because it's a dense set. Therefore, my original A must also have a lot of 3-term arithmetic progressions. And that's the proof of relative Roth theorem. Okay. Of course, I have to explain to you, what are these 2 steps, these 2 ingredients. So, but this is the general outline. It'll be helpful to, and by the way, let me say a word about, so I've so far been mostly just talking about the 3-term case, Roth's theorem. So for Szemeredi's theorem, for a k-term, it turns out that if you want to prove Szemeredi's theorem, it's much easier to prove the 3-term case than to prove the 4-term or longer case. As it turns out, for doing transference, or transferring this result down to the sparse setting, at least the way that we do it, there's no additional difficulty involved besides notational difficulties. Right, so I'm going to show you how to do this for the 3-term case, but if you expand out the notation and make some minor modifications, then you can also use the same technique to prove relative Szemeredi theorem. But I'll just explain what happens to the 3-term case. Okay. So now I want to convert language somewhat. So instead of talking about sets, I want to go from sets to functions. So to have a weighted version of these results. So we saw this before. So this is a counting version of Roth's theorem, such that if you have a dense subset of Z mod n, then it contains a quadratic number of 3APs. Using the counting version of Roth's theorem, we can deduce a weighted version where instead of considering a subset A of Z mod n, we now consider a function from Z mod n to the 0, 1 interval. Okay, so if you're limited to 0 and 1, then these 2 are equivalent. But now I'm relaxing f to take values between 0 and 1. And you can deduce this from this, the first result, up to a change of parameters. So these 2 are equivalent up to a change of parameters. So we'll use the weighted version of Roth's theorem. So this is the dense setting. What does a sparse setting correspond to? So I start with some sparse host set S. And more generally, I'll use some weighted form, which will come in the form of a normalized measure, nu. And nu will be normalized so that it has expected value 1. So for example, if I start with some concrete set S, then I want to take nu to be the indicator function appropriately normalized so that it has expectation 1. A subset of S then would correspond to a function f that is majorized by nu, in the sense that it's less than or equal to nu pointwise. Right? And this condition of A having relative density at least delta in S then corresponds to the expectation of f being at least delta. So this is just a table of translations, what I said earlier. So we started out originally in the world of sets, and now we're going to move to the weighted world, where I now talk about functions. And here's the dense setting, and here's the sparse setting. And if you set nu, the majorizing measure, to be identically 1, then that's precisely the dense setting. Okay. So then the relative Roth theorem, which I stated somewhat informally in the previous slide, now I stated somewhat more formally, and I'll explain what this 3 linear forms condition means in a second. But it says that if you start with a nu, which satisfies this 3 linear forms condition, then every function f majorized by nu and having expectation at least delta has this lower bound on the weighted number of 3 APs. And the C can be taken basically to be the same C up there, because the result transfers over through this transference argument. Right. Everything, of course, provided that n is sufficiently large. Okay, so let me say what this 3 linear forms condition is. And this is basically this thing I mentioned earlier about K222s. Now, let me do this precisely. So I look at this graph. So this is essentially the same graph theoretic construction I made earlier, except that now I put the weights on the edges based on the function majorizing measure nu that I started with. And I want to say that the density of this K222 in this weighted graph is somehow pseudo-random, meaning 1 plus little o 1. Right. So writing it out, so if you look at this graph and I want to count the occurrences of this, so I just write out the expressions, it means precisely that this expression is 1 plus little o 1. And the same is true, so that's an additional assumption, the same is true if any subset of these 12 factors were deleted. So this is the precise statement of our result. Right. Yep. Any questions?
So the error term in that 1 plus 2
Yeah.
1 will have to be a tower of exponentials in...
No, it can be anything that's the case with n. So hidden in here, I'm assuming that there's some, okay, so you take maybe a sequence of these things depending on n, and I want to say that this is something which the case to 0 with n.
So, I mean, when you want to then derive the relative Szemeredi theorem, your assumption on the strength of the 3 form condition will have to be tower exponentially strong in terms of the density.
No, I don't. It depends on how you interpret it. But in at least the way I phrased it here, there's no requirement on how fast is the case.
Right, but there should be a planetary version where if you only
Yeah.
want relative Roth for fixed delta,
Sure.
then the little one should be doesn't need to be arbitrarily less than some threshold.
Right, so then you're asking how large does n need to be sufficiently large?
How small the little one has to be, which is
Okay.
yeah.
Yeah.
The same thing.
Sure, yeah. Okay, so
How about a short tower? It's not
yeah, no, but actually, the only place where you have major loss is in the original. So however, whatever bound you get for the original Roth term or Szemeredi term, that's the major source of loss. And in the transference, we only occurred a polynomial amount of loss because of the arguments used.
So are you using Roth's theorem as a black box? Or
We'll use Roth's theorem as a black box.
Through the Ruggia-Szemeredi proof?
We'll use it as, I'll explain in the slide as well. In what I will present in this talk, we'll use it as a black box. Okay, any other questions? Okay, so that was for the 3-term case, the relative Roth term. For relative Szemeredi term, it's a similar K-linear forms condition. And the K-linear forms condition then says that, well, instead of taking a tripartite graph, now I take a hypergraph. So for k equals to 4, I'm looking at a 4-partite 3-uniform hypergraph. So essentially things corresponding to a simplex. And I put in the weights in a similar manner to how I put on the weights for graphs. So these expressions are chosen so that they form a 4-term AP. And each term depends on only 3 variables. So I construct some weighted hypergraph, and I want the four linear forms condition to say that there's something about the density of the 2 blow-up of the simplex being correct. Right, so it's a natural generalization of what I told you earlier, except now you have to work with hypergraphs. The notationally it gets a bit more complex, but mathematically there's not more difficulty. Okay. So to answer your questions earlier, so there's a couple of papers that we wrote. Right? So where we first found this result, so we wrote up in this paper that we titled A Relative Szemeredi Theorem, where we proved this result through transferring the hypergraph removal lemma. Okay, so this is very expensive, but it is a more general result. Right? So transferring the hypergraph, so transfer means that we assume the hypergraph removal lemma as a black box, and then we transfer it down to a sparse relative setting. So this gives a relative sparse hypergraph removal lemma. Subsequently, I found that you can actually transfer Szemeredi's theorem. So a modification of the argument allows you to transfer Szemeredi's theorem down from the dense setting to the sparse setting. So there, the quantitative bounds on Szemeredi's theorem can be just brought down to the sparse setting.
So that's what you say in the case of three projections that is easier to think about, is that you can say that in a kind of graphs that come up in that reduction, just by the analytical proof of Roth's theorem, those graphs satisfy a triangle removal lemma with a really good bound, not with the Tau of exponentials, but just with a single exponential.
So can you say your question again?
Yeah.
Not sure I understood.
So, like, somehow it seems that the argument that you were sketching was to say, well, let's look at the Ruja.
Right, so that was for motivation. So the reason why I sketched the Ruja Szemeredi was to motivate the graph construction.
Right, but so it's in the US suggested then you just do the same argument, but not with that full tripartite graph, but with some kind of pseudo-random subgraph. And then because the triangle removal lemma is true for the dense graph,
so that's this approach. Right, that's this approach. Right.
But
So
you just need. Okay, maybe this is.
Okay. Okay, maybe we can talk off the line. Yeah. So in comparison, this approach gives a more general result about hypergraph removal lemma in the sparse setting, and this approach is more direct. Now they're not independent. So this paper, I like this paper a lot because it's really short, but it does quote a key fact from a key step from this result. So yeah. So there's a counting lemma, which I'll explain, and that's like the main new advance that we have, and this quotes the counting lemma. So somehow this doesn't actually contain all that much new mathematical content, but it's an outline of how to put things together to give you a very short and direct way of getting the relative Szemeredi theorem. Okay, and
you can prove that counting lemma without referring to graphs, actually.
Sure, yeah.
This is self-contained, the 6 pages?
It's not self-contained at all. Yeah, so it's very much not self-contained. But I'll explain, so the approach that I'm taking in this talk follows this outline. Okay, so I gave a transference slide early on with sets. Now I'm just giving the same slides with functions. So I start with f majorized by nu. So f is some sparse thing, and sparse means that it's unbounded because of the normalization. And there's some dense model theorem which guarantees us that you can approximate f in a certain cut norm, which I'll explain in a second, so that this dense model f tilde is a dense object, so it's bounded. They have the same expectation. And a counting lemma then would guarantee that these two expressions, which are the weighted 3AP counts, they are similar. So, and by the weighted version of Roth's theorem, we know that this is lower bounded, and therefore we have relative Roth's theorem. Okay, so now I need to explain these two steps. What is dense model theorem and what is counting lemma? So let's start with dense model theorem. So in what sense, okay, so I say dense model, so in what sense does this dense model f tilde approximate the sparse object f less than nu? In the previous approach taken by Green-Tao, they used something which is based on the Gauss uniformity norm. And the key difference for us is that we don't use that. We do not use the Gauss uniformity norm. Instead, we'll use the cut norm, which is also known as discrepancy. And yeah, so I'll explain what that is in the next slide. The comparison, so what is the pro and con? with a cut norm, we get a cheaper dense model theorem. So it's the same dense model theorem except applied to a different norm. And because of that, we require fewer pseudo-randomness hypotheses. The trade-off, what we have to pay is that there's now a trickier counting lemma. Right? And so that's really the new thing that we have that allows the simplification. Okay, so the cut norm. So if I start with two weighted bipartite graphs, G and G tilde between X and Y. So the cut norm, which is featured in Fries-Cannon's weak regularity lemma, says that I say that these two weighted graphs are close in cut norm if for every subset A of X and every subset B of Y, let's say if you sum the edge weights between A and B, then the sum of edge weights for G is close to the sum of edge weights for G tilde. And this is true for every A and B. And so written out, it looks like this. That's what it means for two weighted graphs to be close in cut norm. For two functions on Z mod n to be close in cut norm means precisely that I look at that graph that we saw many times that was constructed for the purpose of illustrating Roth's theorem, that graph constructed based on these functions on Z mod n, they are close in cut norm. Right, so that's what I mean by two functions on Z mod n to be close in cut norm. So precisely this expression here, because remember 2x plus y is what arose in the graph theoretic construction. Now this 2 is not important. I can erase both 2's because I can just make a change of variables. But this is the graph that came up in our earlier construction. And this notion is weaker than f and f tilde being close in the Gaussian uniformity norm. Okay. So then the dense model theorem says the following. It says that if you start with a majorizing measure nu, which is close to 1 in cut norm, so this is a statement about pseudo-randomness, and this is implied by the linear forms condition that we had earlier, then the following is true, that if f is majorized by nu, then there's always a dense model, f tilde, which approximates f in cut norm. Okay, so this is a dense model theorem. Okay, so it seems a little strange if you haven't seen it before, like how do you approximate a sparse object by a dense object? Let me just mention a bit of history on this result. So this was used in the original Green-Tao paper, and they used some sort of regularity type energy increment argument. And this result was clarified in a subsequent work by Tao and Ziegler, where they showed that the primes contain arbitrarily long polynomial progressions. And afterwards, there was a simplification of this theorem, so a simplified proof given independently by Gowers and also Rengo, Trevisan, Tusiani, and Vadon, where the proof uses, so Gowers phrased it in terms of a separating hyperplane theorem, whereas Rengo, Trevisan, Tusiani, and Vadon used actually the minimax theorem. And also in both cases, they had to use the Weierstrass polynomial approximation theorem. But this is a very nice and short proof. So this is a very nice and short proof of the dense model theorem.
Is this the same as the Hahn-Banach?
Yeah, that's the Hahn. Actually, so I was looking it up, and I thought this result, Gowers only uses the finite dimensional case of Hahn-Banach, which, is, yeah. And I think that was actually attributed to Minkowski even before Hahn, but anyways. So that's the dense model theorem. Okay, so that was this part of the outline of the transference result. Now I want to talk about what is new for us. That's the counting lemma. Okay, so what is our counting lemma? So first, let me review the classical counting lemma. So a counting lemma is a result that says that if you have two weighted graphs, G and G tilde, if they're close in cut norm, okay, and for the moment, we'll only consider the dense setting. So G and G tilde are both bounded by 1. If G and G tilde are close in cut norm, then they have similar triangle counts. Right. So this is the classical triangle counting lemma. Let me show you a proof of it. It's quite short. Recall what it means for G and G tilde to be close in cut norm. It means that this expression is small. Right? So if I restrict this expression to indicator functions A and B, I can relax these indicator functions to 0, 1, interval 0, 1 valued functions. right? Just because this is a bilinear object, so the extremum always occurs at 0, 1 values. So I can relax it so this is an equivalent. So these two statements are equivalent to each other. So where instead of taking indicator functions, I now take functions taking 0, 1 interval valued. So let me show you that these two expressions are close to each other. I start with the expression for G, which will be highlighted in blue. So this is the triangle counting G. I claim that I can swap out a factor of G by G tilde. Okay? And the reason why this step is true is that if I look at the difference between the two sides and I fix a value of Z, right, so just imagine a fixed value of Z, then the difference between these two sides has precisely this form. So for every fixed value of Z, the difference between the two sides is at most epsilon in absolute value. And if you allow Z to vary, then they're still bounded by at most epsilon in difference. That's just one step. I swap out a single factor by G tilde. Now I swap out the second factor, the same argument applies. And I swap out the third factor and I see that, well, I get what I want. So the difference between these two sides is at most 3 epsilon. Okay, so that's how you prove the dense version of the triangle counting lemma. It's fairly straightforward and fairly quick. But this proof breaks down almost immediately in the sparse setting. Remember, the sparse setting refers to the case when G is unbounded. And when G is unbounded, the first thing I said about these two being close in cut norm, because you can look at that, is no longer true because, well, I can only use A being bounded, and if G is unbounded, I can't use the cut norm anymore. So we need something else. Right? So, and we need some additional conditions in the sparse setting. And the sparse triangle counting lemma that we give says the following. If you assume that one of the G's, right, so the sparse G, is majorized by a nu that satisfies this 3 linear forms condition, so this condition about pseudorandomness with respect to K222s, then G and G tilde, and G tilde is still a dense object. Then G and G tilde being close in cut norm implies that they have similar triangle counts. So this is a new triangle, sparse triangle counting lemma. Okay. So the proof has a few ingredients. There are many, many applications of the Cauchy-Schwarz inequality. Now, this is a standard technique in this area. It's popularized, for example, by Gowers. I won't say too much about that, right? But I won't bore you with too much of the details of repeatedly applying Cauchy-Schwarz. But okay, so that's one of the steps. The new thing for us, the new idea for us, something we call densification, which I'll explain on the next slide. And we also need the proof in the dense case, which I explained on the previous slide. So what is this new densification technique? It's actually quite simple. So you start out wanting to count triangles. Okay, you apply Cauchy-Schwarz in some manner a few times. Now, Cauchy-Schwarz involves some squaring, and squaring gets you, double the vertices. And by the way, so the loss, so why we need a 3 linear forms condition mostly comes from this step, repeated applications of Cauchy-Schwarz. Then that's the most expensive step in terms of pseudorandomness conditions. But after applying Cauchy-Schwarz, let's say a few times in a few different places, one place you might end up is this object, wanting to count this 4 cycle. Okay, so how do you count the 4 cycle? Here's what we do. Let's construct this auxiliary graph G prime. G prime is just the set codegrees. So I put down a complete graph between x and y, a new graph, where I put on the edges the codegrees. The idea is that even though I start out with something which may be sparsely supported, if it's bounded by a pseudo-random graph, the codegrees are going to be much smoother. It's going to be, they're not going to behave nearly as badly as the original graph. And you can view these codegrees almost as if it were a bounded graph. So it behaves like a bounded object. It behaves like a dense object. Now, looking at this expression here for the 4AP count, if I integrate out the z primes, then this is just the triangle count in this new auxiliary graph where I keep the original edge weights but I add in the new co-degree weights as the edge weights for the new graph between x and y. So, okay, so now I'm back at evaluating some triangle counts. So at first it seems like we went around in circles, but I want to do triangle counting. So doing a bunch of Cauchy-Schwarz, I get to count 4 cycles, and this reduces the counting triangles. So it seemed like we went around in a circle, but we gained something really important, which is that one of the edges now behaves like a dense edge, a dense bipartite graph. Now, do this 2 more times. Right? Do this 2 more times, and you convert the problem from the dense setting, from the sparse setting, to the dense setting, which we already know how to handle. And that completes the proof. Well, it's a sketch of the proof of the triangle counting lemma. Okay. And then putting everything together, so I showed you what this dense model theorem is about. Okay, I didn't show you the proof, but I showed you what it's about. And then we have this counting lemma, putting everything together, we get this relative Roth theorem. Okay, so since the original Green-Tao work, there has been several simplifications. So Tao simplified some of the number theoretic estimates that were involved in constructing the pseudo-random host. And the dense model theorem was, the proof was also simplified, as I mentioned early on. And now we putting some new insight into the counting lemma. So there's been several simplifications since the original Green-Tao paper. I think it would be good to collect them into one place. And so we are currently finishing up writing an exposition of the updated exposition of the Green-Tao theorem. And the idea of that this will be a gentle exposition giving a complete and self-contained proof of the Green-Tao theorem that could be used for educational purposes. It's self-contained with one caveat, is that we're going to assume the Szemeredi's theorem as a black box. Right? So we will not be able to contain Szemeredi's theorem in a very short exposition.
It will contain all the number theoretic stuff.
It will also contain the number theoretic estimates. That's right. Yeah. So,
First principles.
assuming rudimentary knowledge. Okay. So, coming soon, hopefully. Okay. So this is my last slide again with the statement of result, and that's all I want to say. Yeah. Thank you.
You have to check these linear form conditions.
Yeah.
Could you say it's scary if you haven't looked at it? How scary is it?
So it depends on what. So what you want to do is to prove the Green-Tao theorem, then okay. So you have to first think about how do you construct this pseudo-random superset or the pseudo-random measure. Okay. So there's some number theoretic work that's involved. It's not too bad. So Terry has simplified some of the since the original Green-Tao paper. It's not too bad. It's not too bad. Like it's clever. It's not too bad. Yeah.
You don't even need the prime number theorem anymore.
Yeah.
Oh, you know?
Chebyshev's theorem. I'm not surprised.
So would you say it's significantly easier to verify your version of the linear forms condition than it is to verify their version of the linear forms condition?
I mean, there's less things to verify. I don't know whether, in retrospect, things are easy once you figure them out. But I mean, there's fewer things to verify.
Is that you'll collide?
So I have a question.
Yeah.
Julia backwards.
Is it possible that the linear form condition alone implies a dense model theorem with respect to the Gauss norm, or is there any non-counter example?
That I'm less familiar with. So, yeah, I mean that's more. I mean, you can look. So Gowers has a paper explaining the paper where he gave the shorter proof of dense model theorem. He went into some of the aspects of. Yeah, I'm not too sure.
So you motivated the appearance of the 2 blow-up of K3 very nicely by saying, I want to be able to tell any should actually be able to count the blow-up of the edge which is before. But it turns out that in a footnote in your paper you actually remarked that the 2 blow-up of the triangle is not exactly what you can count. You can actually get away with something slightly weaker.
Sure.
So
Yeah.
the question is, so
Right. So it's
the
somewhere in
tip
between.
blow up of the triangle would have been a very natural thing, but it's actually not
Right.
exactly what you need. Do you have an explanation for that?
No, actually, so for triangles, you do need a tube blow up. Is that for other graphs, if you want to do removal lemma for other graphs, you can do away something slightly. For triangles, you still need a tube blow up. Yeah, for another graph, you can use I think what we call weak tube blow up, where you save a few of the other edges. But I mean, it's a legitimate question. The amount of pseudo-randomness condition, okay, you definitely need more than just knowing the triangle counts. Right? Just knowing the triangle counts won't get you anything. You need more than that, and we know that tube blow up is enough. So the
Do you
truth,
think this
like,
is a right?
it feels like it, but I'm not sure. I mean, the truth could be somewhere in between, but it certainly feels like a natural condition. Yeah.
So is there a chance that this transference principle, or even more generalized transference principle, will enable to boost up the bounds in the original Szemeredi or Roth theorem or Szemeredi theorem, where the idea would be to start with some not so dense object and to put it pseudo-randomly or pseudo-randomly in a slightly more dense and then in a slightly more dense and so on?
Yeah, that would be very nice, wouldn't it? I think it's an interesting direction to consider, but we had some examples which were not, I mean, they're not necessarily counterexamples, but they raised some skepticism towards that approach. But it's maybe. But yeah, I think it would be, I mean, even for the prime, like, constructing this majorizing measure is a non-trivial task. And yeah, I don't know.
Instead of Theorem, you have another abelian final group. The what theory?
Yeah, so in fact, the hypergraph removal version is it works very well for any groups. Yeah, so I forgot to mention that in this outline, yeah. So in the original Green-Tao paper, they did something which is similar to this, and then subsequently Terry Tao had a paper that shows that the Gaussian primes contains constellations, arbitrary constellations, and that was more similar to this approach here. In fact, we took a lot of the inspiration from those two works, of course.
That seems to be very good.